Imagine a fuel line so inherently dangerous under pressure that Caterpillar engineers decided, you know what, we need to build a completely separate second tube just to catch what happens if the first one fails. Welcome back to The Explainer. Today, we're diving into the C175 engine's double-wall quill tube, a brilliant, absolutely life-saving safety feature. Now, this isn't just some case of over-engineering, right? The stakes here are massively high. When you're managing fuel containment on high-pressure common rail platforms, understanding this architecture is literally the difference between a routine, hey, no sweat, 5-minute visual inspection during a shutdown, and a catastrophic 5-alarm fire right in the engine bay. It's all about taking an incredibly volatile situation and creating a mechanical safety net that catches a problem before it even thinks about escalating. And to understand exactly why that safety net is so crucial, you just have to look at this staggering number straight out of the manual. 180,000 kilopascals. That's just over 26,100 psi. I mean, think about that amount of force for a second. If you were running a bare, single-wall high-pressure line and that seal let go or the line ruptured, it would spray atomized raw fuel directly into a blisteringly hot engine bay. The double-wall design exists entirely to take that severe potential fire hazard and turn it into a safely contained, highly detectable leak.
All right, moving into Section 1, the double-wall solution.
So how exactly do you take 180,000 kilopascals of fluid force and safely contain it if a seal degrades? Well, you use a quill tube. Now, this isn't just a simple pipe. It's a highly specialized double-wall high-pressure fuel line design. You've got the inner tube, which is your workhorse handling the actual delivery of fuel at full rail pressure to the injector, but wrapped completely around that is the outer jacket, and that serves as your secondary containment layer. They have two totally separate jobs. The inner wall is all about performance and power delivery, while the outer wall is dedicated 100% to safety and containment. When we look at the cross-section here, you can see the actual leak path for the injector, the quill tube, and the flow limiter. To maintain a seal under all that constant vibration and insane pressure cycling, there's a metal-to-metal mating surface between the injector bore and the quill tube. But what happens if that metal-to-metal seal degrades over time? Instead of spraying freely everywhere, any escaping fuel is instantly caught. It flows directly into the copper outer wall of the quill tube. This system literally physically routes the escaped, highly pressurized fuel safely away from the danger zone. You'll notice the O-ring and the flutes here. If a leak happens, the fuel is forced into these flutes, travels through the copper outer wall protection, and then into the outer wall of the common rail. That O-ring is absolutely critical. It seals the high-pressure supply line to its corresponding mating surface, ensuring that any stray fuel has absolutely nowhere else to go but exactly where the engineers want it, right into those flutes. Which brings us nicely to Section 2, the early warning system. Because naturally, the next logical question is, okay, once that outer jacket catches all that leaking high-pressure fuel, where exactly does it go? It can't just sit trapped in there forever. Think of it like this. You know the drain pan sitting under your home water heater? You never want to actually see water in that pan, but its entire purpose is to give you an early warning. It catches a slow drip so you can fix it long before your whole basement floods. The quill tube's outer jacket works exactly the same way. The real genius here, the insight people tend to miss, is that this containment system isn't just about preventing a mess. It's a built-in early warning system. It catches internal leaks and routes them externally way before the engine bay can ignite. So a few drops caught early, that's just a scheduled repair. So where do we actually look for this early warning? Well, Caterpillar made it incredibly simple. Gravity intentionally carries all of those contained leaks to one highly specific, highly consistent inspection location for the entire rail system. It's a single drain point, located right under cylinder 1. You don't have to go hunting around checking 16 different hidden pockets. Any leak from any quill tube's outer jacket anywhere along the rail will eventually make its way down to this one visible spot. It turns an invisible internal hazard into a very obvious, easily checkable external sign. Let's put this into practice in Section 3, three-step troubleshooting. Theory is great, for sure, but let's pivot to real-world wrenching. Here's a scenario, and honestly, it's where a lot of techs make a really critical mistake. You're doing a walk-around, you look under cylinder 1, and you see a drop of amber fluid. What's your very first move? Well, a lot of folks see fluid at the fuel rail drain and instantly assume, fuel leak. But skipping the identification step is a massive error. You have to ask yourself, is it fuel or is it oil? Because oil at that location points to an entirely different problem, like a lubrication or seal issue somewhere else. If you just assume it's fuel without verifying, you could literally waste hours chasing the completely wrong repair path.
And that is exactly why there's a rigid, non-negotiable three-step protocol. Step 1, verify the fluid type. Make absolutely 100% sure it is actually fuel. Step 2, if it is fuel, your diagnosis leads straight to inspecting the O-ring seals on the quill tube because we know exactly where that fluid is coming from. And step 3, ensure the hardware is torqued exactly to specification to restore that critical metal-to-metal seal we talked about earlier.
Now, when I say torqued to specification, I mean exactly to this specification. 40 Newton meters or 30 pound-feet. Guys, I cannot stress this enough. Never, ever estimate the torque on a quill tube by feel. This is not a suggestion, it is a strict structural requirement. If you under-torque it, you ruin the metal-to-metal seal, and guess what? It's going to immediately leak under that 180,000 kPa pressure. But on the flip side, if you over-torque it by pulling just a bit too hard, you can permanently warp and damage the sealing surface, completely ruining the component. Let's anchor this to reality. Looking at the actual service manual instructions, it clearly dictates tightening the bolts in a specific numbered sequence, taking it step by step and finishing exactly at 40 Newton meters. This proves that this strict torque spec is an absolute wrench-turning necessity. It is the only way to guarantee the safety architecture operates exactly as intended. All right, wrapping things up in section 4, summary and next stop. So, we've successfully navigated the journey from the high-pressure pump to a fully secured, deeply protected fuel rail. What are the big takeaways? First, 180,000 kilopascals practically demands secondary containment. The double-wall quill tube is a non-negotiable, life-saving design. Second, that single drain under cylinder 1, that's your early warning system. Use it to catch a drip before it becomes a complete disaster. Third, when troubleshooting, always verify if the fluid is fuel or oil before you touch a single wrench. And finally, respect the manual. Never estimate quill tube torque by feel. These are the rigid rules that keep the engines running and, more importantly, keep you safe. We've now safely secured the path all the way to the rail, but the final stage of that fuel's journey is the injector itself, which leaves us with a pretty fascinating question to ponder. Once that perfectly pressurized fuel reaches its destination, how do the C175's injectors manage to deliver multiple, precisely shaped injection events per cylinder, per single stroke? That incredible level of complexity is exactly what we're going to unpack in our next explainer. See you then.